Systems of linear equations. We know what linear equations are. We worked with linear equations with one variable, and we worked with linear equations with two variables. For instance, the linear equation 2x plus y is equal to 5. It's a linear equation because the variables have an exponent of 1. The fact that there's two variables means that this equation has infinitely many solutions. So what a system of linear equation does is it takes two or more equations and it groups them together, called a system. For instance, if you look at example 1, two linear equations where each one has infinitely many solutions, but by putting them together to form a system, looking at that brace on the left hand side, the overall system then will also have solutions. Now, solution to the overall system will be any points that these two equations have in common. For instance, example 1, we're asked to determine if the point -2, -7 is a solution to the system. In order for it to be a solution to the system, it has to be a solution to every equation within the system. So check it. Plug that point into each equation. The first one, 4 times -2 plus -7. We want to see if it's equal to -15, and of course it is. But we just can't stop there. We also have to check the second solution. Substitute the point -2, -7 into the second solution, and you'll see that it's a solution of it as well. So since that point is a solution to every equation within the system, it's a solution to the overall system. Example 2. Same thing, a system of two linear equations. We're asked to determine if the point -1, 5 is a solution to that system. So plug it into each equation. It is a solution to the first equation, but it is not a solution to the second equation. So therefore, it is not a solution to the overall system. So working with these systems of two linear equations, there's basically three possible outcomes when it comes to the solution. And we can see them graphically. If we graph two lines, most lines will simply intersect at one particular point, one point of intersection. Therefore, there'd be one solution to that system. However, another possible outcome would be if the lines never touch or never intersect. In other words, the lines are parallel. Parallel lines in a system means there's no solution to that system. In a third possible outcome, you graph one equation in the system and you graph the second. It is possible that that second equation gives you the exact same line. In other words, the lines lie on top of one another, which means they have every single point in common. So there'd be infinitely many solutions. So three possibilities for solving a system of two linear equations. Most of the time you're simply going to have one solution, but it is possible to have no solution or infinitely many solutions. So primarily what we're going to be asked to do is find the solutions to a system. And we're going to cover a total of three methods in order to do that. The first method is called the graphing method. Basically what we just see here, we're going to graph the lines and find any points in common, any points of intersection. Now, as I said, there are three methods. Some methods work better than others for particular systems, but they all will work for every single system of two linear equations. So example 1, solve using the graphing method. Just graph each equation. The first equation, y is equal to 3x plus 1, y-intercept form. The y-intercept is 0. The slope is 3, so we go up 3 to the right 1, and we sketch that line. The second equation, y is equal to 3. The fact that it only has the variable y means it's going to be a horizontal line through 3. So obviously, sketching those lines, we see that there's only one point of intersection. So there's only one solution to the system. So all we have to do is find it. It looks like it's at the point 1, 3. But just to make sure, we can of course plug those values into the equations to double check like we did a few minutes ago. And we'll find that yes, it is the solution to that system. The point 1, 3, one point of intersection. Example 2. Given this system of two linear equations, solve it using the graphing method. So the first equation, slope-intercept form, the y-intercept is 1, the slope is 2, up 2 to the right 1, and we sketch that line. The second equation is not in slope-intercept form, so the first thing we want to do is get it in the slope-intercept form. Y is equal to 1/2 x plus 1/2. So the y-intercept here, 1/2, the slope 1/2, so we go up 1 to the right 2. Sketch the line passing through those 2 points. And once again, we obviously see this system only has one solution. All we have to do is find that point of intersection, which in this case is going to be a little difficult, if not near impossible, because first of all, we're doing it by hand, which means there's going to be a little error. Secondly, the point of intersection is a decimal of a fraction, so we'd have to get pretty lucky to be able to determine exactly where that point of intersection is. We could use a graphing calculator, graph the lines, and find the point of intersection. But as we see this example, this is why we do not really rely on the graphing method too much. Sometimes it's, at least doing it by hand, is almost impossible to find the point of intersection. Now if you did find it using the graphing calculator, it would work out to be -1/3, +1/3. So in summary, systems of linear equations, we're primarily going to be working with systems of two linear equations, although you could have systems with more than two equations, and there could certainly have systems with equations other than linear equations. But for now, we're just going to be working with the most basic systems of two linear equations. We know what the solution to a system is, what they look like: one solution, no solution, or infinitely many solutions. And we know one method in order to find these solutions, the graphing method.